All right, welcome everyone to our, I think, fourth session of the Future Leaders in Robotics and AI Celebrating Diversity and Innovation seminar series. It is sponsored by the Microsoft DC Metro Engineering. And if you want to find any additional information, please click or go to that link in our website. All right, our speakers for today are, and I'll start with our first speaker and then introduce our second speaker later on. Our first speaker is Anushri Dixit. She's a postdoctoral researcher in the Department of Mechanical and Aerospace Engineering at Princeton University. She earned her PhD in Control and Dynamical Systems from Caltech in 2023 and her BS in Electrical Engineering from Georgia Tech in 2017. Her research is focused on motion planning and control of robots in unstructured environments while accounting for uncertainty in a principled manner. Her work on risk-aware methodologies for planning has been deployed on various robotic platforms as part of Team CoStar's effort in the DARPA Subterranean Challenge, and she has received the Outstanding Student Paper Award at the Conference on Decision and Control, the Best Student Paper Award at the Conference of Robot Learning, and was selected as a Rising Star in Data Science by the University of Chicago. And she is about to start in July 2024 an assistant professor position at the University of California, Los Angeles. All right, with that, go ahead, Anushri.
Can you see my screen? Perfect. Thank you for the introduction, Cecilia. Hi, everyone. My name is Anushri, and today I'll be talking a little bit about thinking about robot safety and generalization in a time when, we're thinking about deploying all of these different systems that are based on like foundation models and learned models. Okay, so robots can perform a lot of complex tasks. Over here in the first video, what you see is Tesla Autopilot totally autonomously navigating through a suburban setting. You can see it detecting through its perception system a variety of agents in the environment, like other cars, pedestrians, bicyclists, and it's able to like pretty successfully navigate through this environment, which is amazing. In the second video, what you're going to see is Google DeepMind's SayCan work, where given a language instruction, the robot is able to actually use a large language model, kind of interpret the human instruction, saying, okay, I spilled my Coke on the table. Can you bring me something to help clean it up and throw the Coke can away? And the robot is able to combine that language understanding with an understanding of what itself it can do, so what tasks it is capable of, just the affordance, and then it's able to combine both of those things to then find a Coke can, pick it up, throw it into the trash can, and then bring a sponge to the user. Again, this is really amazing because it's able to do all of this totally autonomously. But reliability is still a pretty big issue, I would say. So now here you can see Tesla's Autopilot is unable to avoid a collision with like this fake pedestrian on the road because of a failure of its perception system. And then in the next video, you're going to see a similar like SayCan video where given a user input of I left out my Coke, apple in water, can you throw it away? And then bring me a sponge. So far, as you can see, the robot has, found an apple, put it near the trash can, same with the water bottle. And the next thing it's trying to do is it's trying to find the Pepsi and throw it away. But actually, if you look at the user instruction, it's saying, throw away the Coke, not the Pepsi. Clearly, this is a failure of the language understanding of this model. You may wonder, like, okay, this is fine. These are like not as big, but this actually really affects us in the real world. So Cruise had to recall all of its driverless cars after a pedestrian was kind of hit and dragged by one of its cars late last year. And that was due to a failure of its collision detection system. Similarly, we actually tried this similar example where we said, there's a metal bowl and a plastic bowl on this small counter. Suppose you're a robot and the human asks you to put the bowl on the counter into the microwave, and we ask the LLM, what would you do? Which bowl would you pick up? And the LLM very confidently says, I would pick up the metal bowl as it's more likely to be able to withstand the heat from the microwave without melting or getting damaged. Which is not something, again, you don't want robots putting metal bowls in microwaves because that can quickly lead to a lot of dangerous situation. So the question I really want to ask today is, how can we guarantee that the robots that we interact with are reliable in new environments? And for that, I want us today to consider a modular autonomy stack. So consider you have a modular perception and planning framework where it may be given a task. In this case, the same example that I used before, put bowl in the microwave. The robot can then interpret the human commands using an LLM, use a perception module to interpret the environment, and then a planning module to make decisions based on the human instruction and perceptual outputs. If you're using an LLM to interpret the human instruction, there can be errors in terms of the actions that the robot ends up taking, because now the robot kind of interprets the environment incorrectly, or like plans the incorrect thing because of the errors in your LLM model, and that can lead to failures. Similarly, you may have a learned perception system, an off-the-shelf maybe object detection module. Here you can see this robot is kind of navigating using a camera in this office-like environment. It's doing object detection, so it's trying to detect where the objects are. This is what it's seeing. And the red boxes that you see are the predictions from the off-the-shelf perception module, and the blue boxes are the real locations of the objects. You can see here, like this chair is hidden, kind of occluded by the chair in front of it. And that's why that kind of leads to perception errors. So even if actually you had a safe planner, because of this perception error, there's going to be a downstream failure, even if you had something that was guaranteed to act safely because of perception errors. So really what we want to consider today is, how do you quantify the uncertainty of learned black box models without making too many assumptions? A lot of the times when you consider such black box models, there's a heuristic and sometimes actually no notion of uncertainty. Another challenge that arises is that the environments we deploy these models in may be different from the training data set, for robotic applications. For example, here, let me just mute this. Here you can see this Tesla, again, is detecting the setting sun as a yellow light in the middle of the road. And finally, another challenge, which is maybe a little more subtle, is that the closed loop behavior of your robot actually may lead to a different distribution of observations than what you've accounted for in your uncertainty quantification. So today, I want to focus on uncertainty quantification for LLM-based planners and then perception-based navigation. Both of these are learned modules that we'll be considering. So let's start with LLM-based planners. So really what we want is an LLM to interpret the human instruction and make plans for the robot. We want, of course, for the robot to behave safely, and then there are challenges associated with that. One being that LLMs tend to make mistakes. And the second being, a lot of the times there's actually ambiguity in the language instruction. So in this case, for instance, the human is not clear which bowl, metal or plastic, the robot should be placing in the microwave. That's kind of ambiguous in terms of the instruction. The goal here is that the robot should ask the human for help when it's actually unsure of what to do. Okay, how can we do this? The way we think about this is by asking the LLM to generate a set of possible plans. It's almost like a multiple choice question answering setup where you're choosing amongst the next possible steps. So as you can see here, the LLM then makes some next possible step predictions. So given the human instruction, place the ball in the microwave, given the robot observations, the LLM says I could do any one of these four things. It generates these four possible options, and it has some next token probabilities associated with which one of these is correct, which one of these options is correct. And what we're going to do is we're going to use this statistical technique called conformal prediction, and this is abbreviated as CP here, to calibrate the uncertainty of the large language model. Okay, how do we do this? Really, very, very briefly, what conformal prediction does is you have some pre-trained black box potentially model. We call it F hat. And then you have some additional calibration data set of input and output labels. So what does this mean? In our case, this would mean the language instruction is your input, and then the correct option amongst the four options that I showed you is the true label. So you have this data set where you're kind of labeling what the right thing to do is given a bunch of instructions, and n instructions, for instance. And once you perform conformal prediction, the output that you get is a prediction set that is statistically guaranteed to be correct. Okay. For this calibration data set, we define a nonconformity score. And in our case, we use the next token probability of the true class. So the next token probability is what you're using as F hat in this case. And your nonconformity score given by S is your is this notion of how good your LLM prediction is. So really what it's doing is this notion of how well it conforms, to this calibration data set. How good your LLM is performing is defined by this non-conformity score, because it's performing poorly if your next token predictions are low for the true class, for the right thing to do. Okay. So what we do is we collect these nonconformity scores for every sample in our calibration data set. So we're doing this offline. And once we've computed these nonconformity scores, we arrange them in this ascending order. And the rough idea here is we get this alpha quantile. It's not exactly the alpha quantile. It's adjusted based on the number of samples you have in your calibration data set. There's some sort of an adjusted quantile that you're finding, such that a new nonconformity score that is sampled from this calibration data set is guaranteed to be less than this quantile with some probability. Okay, how is this useful? It gives you this prediction set. Really what this says is once you've done an offline calibration of your LLM, you have this quantile, you will now choose all of the outputs that have all of your options that have a next token probability that is greater than 1 minus Q hat, okay? And so that's your prediction set. So in this case, all of the options that are greater than this 1 minus Q hat that you've constructed are possibly correct. And so the guarantee that you get is the probability that your next step action is correct and lies in the set that you're predicting is greater than 1 minus alpha. This is a very, very rough idea of conformal prediction. I'll just very quickly show you what that looks like for our example. You really have a set of instructions, like n possible instructions. And for each of these, you do this like multiple choice question answering like setup, and you label manually which is the right thing to do. And that gives you some sense of how well your LLM planner is performing in this calibration distribution. You arrange this, you get this threshold using your nonconformity scores, and then you actually use this threshold online. And that's all you have to do. You have to compute this threshold offline using your calibration data set and then use it online. The same example that I showed you before, place the ball in the microwave. The robot is able to make observations of what it sees, and it has some context. It generates possible next steps. In this case, put the plastic ball in the microwave, metal ball in the microwave, so on. Conformal prediction threshold, in our case from offline calibration, is 0.21. And so we include all of these possible options that have the next token probability above this threshold. So at test time, the guarantee that we get is that the correct plan is one of these two options with probability 1. Well, in this case, the set size is greater than 1. It's not exactly 1, so it's actually not sure which of these two options is correct. So it asks for help. It says which one, metal ball or the plastic ball. And then the human is able to clarify, oh, you should pick up the plastic one. So how does this look like? Very quickly.
Hey, robots, could you put the bowl on a small counter in the microwave?
Should I pick up the metal bowl or the plastic bowl?
Pick up the plastic bowl, please.
So as you can see here, then given this calibration, the LLM planner is able to ask for help when it needs to. I'm not going to go too much into the details of our results, but we also show that we ask for a minimal amount of help and we outperform some of the baselines that we've considered in our paper. The next thing I want to talk about is how to use a similar, like the same uncertainty quantification technique, but now thinking about perception-based navigation. So this was the initial modular autonomy stack that I had shown you, where perception errors when you were using off-the-shelf perception models led to downstream failures. So the goal, again, is to calibrate our perception model, any off-the-shelf perception model, such that the new calibrated perception model is statistically guaranteed to be correct in previously unseen environments. And hence, when you use it in conjunction with a safe planner, you get an end-to-end statistical assurance on safety. So to obtain this assurance, again, we calibrate the perception model error of the pre-trained system by collecting the perception errors in many different environments, and then we use conformal prediction. In this case, the nonconformity score is a function of the perception error. Previously, it was a function of the next token probability. In this case, what we do is we say, okay, in our calibration data set of different environments, let's make predictions using the off-the-shelf perception module. These are the blue predictions, and compare it to the actual location of the object. And what we try to do is we get this minimum inflation, delta Q, that we need to make to the union of these red predictions, the predictions from the off-the-shelf module, such that the ground truth location of the object is completely enclosed by this inflated output. So then the nonconformity score that we use is we consider a set of n environments, and in each environment from every state, we compute this perception error, and our nonconformity score is the worst perception error across all states. And so now the bound that you get using conformal prediction is for the worst perception error in the new environment. Okay, and so what we do is we use this offline calibration procedure, and it gives us a guarantee on the correctness of the calibrated perception model. So it's a new inflated output. So you take essentially this prediction from the off-the-shelf module, and you add this delta Q, this inflation, the level of this inflation you get using conformal prediction. And then the guarantee that you get is for all states in any new environment, the calibrated perception system will enclose the ground truth location of the true objects in the environment. And this will hold with probability 1 minus alpha. So then we use this online. We use this calibrated perceptual output online, and we use it in conjunction with a safe planner. And because the calibrated perception system is guaranteed to be correct, now when you use it in conjunction with a safe planner, we can actually ensure and guarantee end-to-end safety. A question that you may be asking is whether we can make this calibration procedure less conservative, and the answer is yes. And the intuition there is because this calibrated perception system is correct from every state in the environment, the intersection of these predictions also has to be correct from every state. So let's look at this as an example. These light red boxes that you're seeing are the inflated outputs from the calibrated perception system. The red boxes are the true locations. So you can see it's a little bit conservative using this like calibration procedure. The blue region is the free space. At the next time step, this is the prediction it makes, this light red box. But because of the way we've generated this guarantee, both of these outputs have to be correct. So you consider the intersection of the predicted occupied space over time. That has to be correct at all times. So this kind of filter of your predictions gives you less and less conservative behavior. And in this case, over time, you can see that this kind of converges through the true locations of the object. This method we can use in conjunction with really any sampling-based safe planner. We use fast marching tree start. We account for the robot dynamics through SysID, and we account for the states from which the collisions will happen, regardless of the control input applied, and we call this the inevitable collision set. So it's a sampling-based planner that we use. When we don't account for the worst case perception error across all states during offline calibration, and instead you consider just the average perception error as a baseline, you can see that even if it's calibrated using conformal prediction, in this case, you can see that there are a lot of misdetections of the obstacles because of the closed loop behavior of the robot. So you can see that the objects are still not exactly detected correctly every time. And this kind of leads to this downstream failure that I alluded to earlier, where over time, since the occupied space is incorrectly classified as free, the robot kind of, even though it's a safe planner, the robot still plans through this occupied space. On the other hand, our method, we call it Perceive with Confidence, or PwC, is able to predict these like inflated calibrated outputs which hold from every state. So you can see they're a little larger, but when you use it in conjunction with our filter that I mentioned, you can see that actually the free space is not as conservative as it would be if you just did the worst case calibration. So you get this guarantee that holds across all states. It's not overly conservative, which is really great. So this guarantee holds with probability 1 minus alpha, the safety guarantee, in any new environment that is sampled from this calibration distribution. Very quickly, I want to show you some examples of this. Again, I'm not going to go into the results. You can look at our paper for that. But when these misdetected obstacles are not on the path to the goal, both baseline and our method PwC are successful. But actually, in the cases when the path to the goal is not completely free, the baselines tend to fail because this misdetection now suddenly becomes important and leads to failures, while our method is still able to perform safely. And we're also able to account for occluded obstacles and occluded goals and still navigate safely around them. So just to conclude very quickly, I just want to give you some of my thoughts on both of these things that I've shown you today. Increasingly, we're relying on learned models in robotics. And I feel like this is great because our robots gain a lot of new skills, agility, and adaptability. But I think it's really important to think about what we may end up losing in the process, which is a lot of the times safety and explainability. So I think it's important to consider principled ways in which robotic systems can use these learned models without sacrificing safety or performance, which is really important. And what I showed you today using conformal prediction is just one of the ways of doing that. And I'd be happy to take any questions. I'll leave you with papers that I discussed today and a rough overview of what I discussed.
Thank you. I don't think you can hear our speaker, so I'll clap for everyone here. If you have any questions, please feel free to use the Q&A feature, and I'll read the questions for our speaker. I'll start with a question from Levi Souza. So the question is, what are your thoughts on verifying the output of the LLM using physical or geometric properties, such as those that can be factored into traditional physics or graphics engines?
I'm not totally sure I understand the questions. I'm just like kind of thinking out loud what this means. So verifying the output of the LLM using physical or jump. Could you give me an example of that potentially? I'm not sure if I guess.
We wait for the example. I'll ask
No,
you
yeah. Sorry.
another question, and then we can go back to this one. So for your first example, and I'm sort of not in this area, so this may be a fuzzy question, but imagine that you have an error in perception and you're not detecting the plastic ball, you're just looking at the metal ball. Is there a way for your system to tell, oh, this is a metal ball, the chances are not very high, there's a good chance that I'm missing something here? Is that something that you can implement in your system?
No, not right now. Right now, it kind of assumes this, and I feel like this is a really important question as well. It kind of assumes that you have, the first part assumes you have perfect perceptual information, and the guarantee kind of holds with that assumption. But you're absolutely right. If it doesn't even detect, then it's probably going to either A, fail if it's just confident about one of the options, because then the prediction set is a singleton, or B, if these kind of examples are accounted for in your calibration, then what ends up happening is that there's an option E of none of the above, which is also true. So then it kind of pushes your calibration threshold in the direction in which it's less confident. So it kind of is higher, I guess. You have to be, the LLM output has to be super confident, and only then can it. So I imagine that the calibration procedure could also potentially account for that. But right now, we are assuming that the perception outputs are exactly right. So that's a great question.
Great, thank you. I think you have the example there if you want to reply that one, and then I have another question from Michael.
Yeah. So the example here is suppose that the LLM proposal is pick up the cup, and then the second one is pick up the boulder. Both are given with high probability due to the failure of the LLM. A simulator would allow determining in a provably correct way that picking up I see. Yeah, great question. I think this kind of goes back to this notion of affordance, which I talked about, that Google DeepMind's SayCan work also looks at, is okay, what can having a notion absolutely of like what you can pick up versus not, and combining that with the LLM generated possible next steps is absolutely crucial. And that's not something we do, but I think, yeah, that would be something that would be really nice to be able to incorporate. And I don't see why you couldn't incorporate that. I think just having a notion of both of these language outputs, likelihood of what's right, versus also an affordance of like what the robot can actually do, and combining that into like a new nonconformity score, and you doing calibration using that is one guess potentially of how you could account for that. Yeah.
Thank you. And the question from Michael, it seems that some problems would have a big drop when you get to the set of unlikely next tokens. So in the bowl and microwave example, there were 2 high probability options, while others may be more gradual with a slow fall off and many different options. Did you have any experiences about the types of problems that are quick fall versus a slower fall, and any ideas of what to do for the cases where there's a sort of slower fall in that probability?
Yeah. So what this is really doing is just it's just finding a threshold, and it's just like a cutoff that it's finding. Anything above that, you include. Anything below that, you don't include. If you have an LLM that's really bad, then that's going to be kind of jumbled up, and that threshold again is going to be lower. I'm not sure if this totally answers your question. That's my intuition. It's just that threshold is just giving you some notion of how good So it's going to get worse if your LLM is worse. If your LLM was like really good and it was really confidently outputting the correct thing, that threshold would get higher and you would ask for help less and less. But there's really no, there's no continuous way of kind of saying, oh, these are pretty close. I mean, if it was like a 0.21 threshold and you had two next token probabilities of like 0.22 versus 0.19, yeah, one's not going to be included versus the other. So there's not that notion, I think, that you're alluding to right now, at least. And I'm not sure, I'm trying to think. Yeah, I'm not totally sure that the setup, again, you'll have to play around, I think, with the nonconformity score a little bit to figure out how to make it more gradual. But at the end of the day, it's like a thresholding thing. Yeah.
Great, thank you.